We have already introduced the techniques for video shot change detection, and right now we will go to scene change detection. In contrast to video shots, the definition of video shot would be the video segment captured by a camera turning on until a camera turning off, and this often occurs when we just want to take one specific scene or one specific object. And when we try to take another object, we often, as a director, we often have to turn off a camera and direct to the new object and turn on the camera. So there will be a shot change. But in scene change, the definition of a scene is usually a collection of video frames which belong to the same semantic meanings. Usually a scene consists of many video shots. For example, in a classroom environment, the camera may capture the teacher first, and then capture the student's name, and then turn to capture the teacher again, and then turn to capture the student. Okay, so in such video sequence, we have several video shots. Okay, so teacher shot number 1, student shot number 2, teacher shot number 3, and the student shot number 4. But basically, all these video shots occur in the same scene, in the same place, and they represent the same semantics. Okay, so basically these 4 video shots belong to the same video scene. So in the following slides, we will introduce the technique to detect video scene change, and we will introduce this paper published in 1998, and this is also a very canonical paper to detect video scene. And the author is actually also from Taiwan, and he is a professor in Princeton University. And this paper was published in Computer Vision and Image Understanding, which is also a top journal of the computer vision field. So we first describe several observations. So shots in a scene are often repetitive, as we mentioned before. In a classroom environment, the teacher shot and the student shot may occur frequently and repeatedly. And we are able to classify shots by grouping shots of similar visual content. So we still assume that the video shot capturing at the same place or capturing similar semantics would also have similar visual contents. So often, a scene is made up of temporally adjacent shots indicating their interrelationship. So we want to group temporally adjacent and visually similar video shots in this task. So now the problem is how to measure the similarity between video shots. In video shot change detection, we have already mentioned how to measure the similarity or distance between video frames. And right now we want to define how to calculate the similarity between video shots. And actually, the idea is quite similar. So given 2 video shots, SI and SJ, and assume that SI begin at EI and begin at BI and end at EI, and SJ begin at BJ and end at EJ. Okay, we said that SI, SJ are similar if there exists a pair of similar frame FM and FN. So if there is a frame FM from SI and another frame FN from SJ, if FM and FN are similar, we can say that SI and SJ are similar. Okay, so basically the idea is we reduce the similarity between video shots, reduce it into similarity between video frames. Okay, so this is the first definition. The second definition is the dissimilarity between SI and SA. The dissimilarity is equal to distance. Okay, so how can we measure the distance between two shots? So the idea is we just compare any pairs between them, any frame pair between these two video shots, and find the minimum one. Okay, so here we may compare the first frame, the distance between the first frame and the first frame of SJ, the first frame of the SI, and the second frame of SJ, the distance between the first frame of SI and the third frame of SJ, and so on. And basically, we will calculate the distance between all the combination and find the minimum one to be the distance between SI and SJ. And how can we calculate the distance between video frames? Basically, we have we have many variations. Okay, you can also calculate the distance based on all we have mentioned for video shot change. So here we just take two examples. The first one is we can calculate the distance based on color histogram intersection. Okay, so we can describe II and IJ. These are two frames extract from SI and SJ respectively, and we describe both of them by color histogram. So for example, the histogram for II maybe like this, and the histogram between IJ maybe this. Okay, so the so-called histogram intersection is we compare beam by beam and find the intersection. For example, the first beam, maybe the first beam here is maybe 3, and the first beam here maybe 1. So the intersection of the first beams are only 1. Okay, and we compare the second beam. The second beam may be 5. Here the second beam maybe 3. Okay, so the intersection is 3, and so on. So we can expect that if these two color histograms are very similar, the intersection would be also large. Okay, so basically histogram intersection is kind of similarity, and here we try to calculate the distance. So we use 1 minus the average distance, the average similarity, so we can get the distance. Okay, so based on such simple calculation, we can calculate the distance between any two video frames. So this is one method. Another simple method is called luminous projection. This is also very simple. That means we project, we can do horizontal projection or vertical projection of video frame. For example, here this is a video frame, and if we do the horizontal projection, we just aggregate all the intensity value for each row. So we may get a horizontal projection like this. That means at this row we have more pixels with larger intensity, so that we can have a higher projected value. Okay, so we can do horizontal projection as well as vertical projection. So we also can do the vertical projection. So we can describe a video frame based on these two projections, and then we can compare two video frames we can calculate the distance between horizontal projection as well as vertical projection and the sum together to measure the distance between two video frames. It would be very computational expensive if we compare all the pair combination between two video shots. So usually we don't compare all of the possible combination. We would like to select some representative video frames to represent the video shot so that we can largely reduce the numbers of distance calculation. So how can we select the representative video frame? So in the following, such kinds of frame are usually called as the key frames. Okay, so here is one simple method. Given the video shot SA starting from FB plus 1 and so on, and we let RA denote the set of representative frame. Initially, we pick FB into this set, and then we compare the following frame to see whether the frame is significant different from current selected video frames, current selected keyframes. If so, we pick the new one into this set and update the set. Okay, so basically the algorithm is quite simple here, and the idea is quite simple. For example, the starting frame is FB, and we will first check FB plus 1. We compare the distance between FB and FB plus 1. If the distance is larger than a threshold epsilon, then we also take FB plus 1 to the set. Okay, but usually in a very short time, FB and FB plus 1 would be quite similar. So we keep going. We select this one, or we take FB plus 2 and compare the distance and so on. Maybe until Fi, when some frame Fi, the distance between Fi and the FB is larger than epsilon, then we also take Fi as a keyframe. And then we keep going. When we take some frame Fj, if the distance between Fj and Fi larger than epsilon, we also take Fj as the keyframe, and so on. So this is a simple way to select the representative video frame. And according to their experiment, only 2% to 5% of frames are needed in comparison to achieve good matching result. Okay, so we can just extract video frames to do so, to calculate the similarity. And in addition to temporal subsampling, so the method mentioned above is a temporal subsampling, because we don't take all the video frames. Okay. In addition to temporal subsampling, spatial subsampling can also be used to improve matching efficiency. The so-called spatial subsampling is resizing. So if the original frame is like this, we can sample maybe one pixel for every 4 pixels. So we can reduce this pixel, this image as like this. Okay, just 1/4 size of the original one. So we can largely reduce the image size, and then based on the resized image, we can further accelerate distance calculation. After calculating the distance between video shots, now we are ready to cluster similar video shots. The idea is the shots in the same cluster should be similar. and any other shot outside the cluster must have a distance greater than the distance between any shot in the cluster. Okay, so here is the mathematical definition. So assume that there is a cluster here, and assume that y and z belong to the same cluster, and the epsilon I means for all video shots belonging to the same cluster, we can calculate the distance between them. Okay, after calculating the distance between video shots, now we are ready to cluster similar video shot together. For any other shot outside the cluster must have a distance greater than the distance between any shot in the cluster. That means if there is a cluster here, and there are several video shots inside this belonging to this cluster. So for a cluster outside, for a video shot outside this cluster, the distance between any shot inside the cluster should be smaller than the distance between one of them to the video shot outside the cluster. Okay, mathematically we can define it like this. So for the video shot belonging to the same cluster, for any two video shots, we compare their distance. For example, these two, these two, these two, these two, and these two, and so on. And we can pick one pair of them that cause the largest distance. That would be maybe this one, and this one. So the distance between the pair of video shots that cause the largest distance is called epsilon I. So here the epsilon I is this. Okay, and the idea is for all the video shot outside the cluster, the distance between any of them, d, should be larger than epsilon I. Okay, so mathematically we can define it like this: dxw is greater than epsilon I if w belongs to another cluster. Okay, so if we are friends, we should be close, very close. For those who are not our friend, the distance between he and us should be larger than us. Okay, so that's the basic idea. So now, how do we cluster video shots? The idea is we first, so given a set of video shots, okay, we use one node to represent a video shot. So we just compare the distance between them pair by pair. So we first find the pair that has this distance. So we may find these two. Okay, we may find this pair, and then we cluster them together. And then we calculate the distance. The same process keeps going. So we may find this pair has the distance. Okay, and then we keep this again and again. But one problem arises. How do we measure the distance between this video shot and this cluster? Okay, so we also need to define the distance between two clusters, and here is the definition. So given two clusters Ci and Cj, we just measure their distance based on the component in these two clusters, and we compare all of them and use the maximum value to define the distance between two clusters. We can also make an illustration here. So maybe this is Ci, this is Cj, and there are several elements here. Okay, so when we try to measure the distance between Ci and Cj, we compare all the possible combination, all the possible pairs. For example, here, 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 and so on. And among these pairs combination, we take the maximum distance, like maybe that would be this one and this one. So we use this distance as the distance between Ci and Cj. Okay, so based on such definition, we can calculate any two clusters. Okay, and so we go back to the algorithm. We can compare this video shot or this cluster and this cluster. We can compare this cluster, or even we can compare these two clusters. Okay, so using the shot pair in which two shots are in two different clusters, they has the least dissimilarity value. Okay, and dissimilarity between two clusters should be updated at each iteration. So we can now cluster these three video shots together, and so on. And here is the algorithm. So initially, given n video shots, we just initial one video shot as a cluster. Okay, and then we keep merging similar video shots. Okay, the stop condition is if the distance between different clusters is larger than the threshold, we stop. Or the numbers of clusters is equal to 1. That means all video shots are clustered together. Okay, this is stop condition. And for each step, we just find the least distance pair of cluster and merge R and S into a new cluster. In addition to considering visual similarity, we also have to consider temporal relationship between video shots, because any two shots that are far apart in time, even if they share similar visual content, they may represent different contents or occur in different scenes. So that we still have to impose time constraint to cluster not only visually similar video shots, but also temporally adjacent video shots. So here is the constraint of temporal distance. So temporal distance between two shots can be defined like this. So we have already know that Si begin at Bi and at Ei. Sj begin at Bj and at Ej. So the temporal distance between two shots is defined like minimum between of the minimum among Bj minus Ei or Bi minus Ej. Bj minus Ei is this distance, and Bi minus Ej is this distance, and we take the minimum to be the temporal distance between these two video shots. And here we write this because we don't know whether Si or Sj appear first. Okay, so here we define the time distance, and the criteria to cluster video shots is like this. We need to make the video shots belong to the same cluster. The distance between them are all less than t. That means for this video shot, there are for this cluster, for many video shots, we can calculate the time distance between them. And all possible pair have time distance less than t, so that they can cluster together. Okay, so this part is the time-based constraint, and this part is the visual similarity. Okay, as we mentioned above. So right now we have already clustered visually similar and temporally adjacent video shots together. And the next step for us to detect a scene change is to construct a scene transition graph. Okay, a scene transition graph is a directed graph with the property VEF, where E is a node. Each node represents a cluster. E is a directed edge that can be drawn from node U to W if there is a shot represented by node U that immediately precedes any shot represented by node W. So the directed edge represents the temporal relationship between different clusters. Okay. And the F is a mapping that partitions the set of shots into clusters. So basically, F is a mapping, okay, mapping shots into clusters. And scene transition graph is able to represent compactly the structure of shot and the temporal flow of the story for many video programs. So here is an example. Assume that we have a video and it consists of 9 shots, and actually these 9 shots belong to 3 scenes. So we can see in this video, at first there is a meeting. So at the meeting, this is the first scene, and it consists of 3 video shots. And then go to the office, this belongs to the second scene. And then go to meeting again, this is the third scene. Okay, by clustering similar and temporal adjacent video shots, we get the following result. So the cluster one consists of these 2 video shots. We can see that these 2 are visually similar. The second cluster have 3 video shots. The third one, the fourth one, and the fifth one. Okay, and then based on this cluster information as well as the temporal relationship, we can construct the scene transition graph like this. So here we see that the first shot belongs to C1. So C1 is here, and then go to S2. S2 belongs to the second cluster. So we see that there is a shot immediately in C1. There is a shot in C1 immediately precede a shot in C2. So there is a directed edge pointing from C1 to C2. Okay, so this is why there is a directed edge pointing from C1 to C2. And then S3 belong to C1 again. So from here we have a shot S2 belonging to C2, point to immediately precede S3 belonging to C1. So there is also a direct edge from C2 to C1. And then we go S4. S4 belong to C3, so C1 point to C3. S5, another S5. S5 is another cluster called C4. So here, point to this one, and then go back to this one because S5 precede S6, and then go to S7. S7 belong to the second cluster, so direct C3 has a direct edge pointing to C2, and then S8 belong to C5. Okay, so C5 is here. We have a edge from C2 to C5, and then from C5 to C2 again. So this is the whole STG describing the structure of the video. Okay, the structure represent visual similarity as well as temporal, the time flow of the video. So based on STG, we try to segment STG so that for each subgraph may represent a video scene. So how do we divide the STG? We have to find the so-called cut edge. Okay, the cut edge, an edge is a cut edge if when it is removed, resolved in two disconnected graphs. So here is an example. We have a graph here. If we cut this edge, the whole graph will be divided into two disconnected subgraphs. Okay, and for this one, we can also cut this one. So if we cut this edge, we can also divide the whole graph into disconnected subgraphs. Okay, so these are cut edge. And for each STG, we try to detect cut edge and do cutting so that an STG can be divided into several subgraphics, just like this. So the STG we mentioned above, we can find that the edge from C1 to C3 is a cut edge. We can cut this one. The edge from C3 to C5 is a cut edge. We can cut this one. So if we cut these two edges, we have a subgraph consisting of C1 and C2, another subgraph consisting of C3 and C4, and another subgraph consisting C5 and C6. So these three subgraphs represent three different scenes. So this is how the author proposed to use STG to do scene change detection. So here is the whole framework. Given a video, they detect video shot change first. So the first step is shot segmentation. And then they do time constraint clustering. Okay, as we mentioned above. And then they build STG. And then they do scene segmentation. So following this diagram, so given the video, they do shot change detection. So we have 9 shots. And then we cluster. And then we build the STG and find the cutting edge to divide the STG into subgraphics, which represent video scenes. We now discuss the inference of parameters. In the process mentioned above, we have 2 parameters. The first one is delta. Delta determines the cluster based on visual distance. So this is used to determine whether the clustering process would be stopped or not. If the distance between cluster is larger than delta, we will stop the clustering process. The second parameter is T. This parameter is for time-based constraint. That means if the temporal distance between video shots belonging to the cluster should be less than T. Okay. Without the knowledge of how long each individual scene lasts, T is usually cannot be approximately well. If T is too large, then shots from different scenes may be clustered together. Okay. If T is too small, then shots in the same scene may be separated into different scenes. Okay, so it's difficult to determine the parameter t, and also the parameter may be content dependent. But basically, it's less detrimental to have several story units represent a scene than to have one story unit represent several scenes. That means we human beings prefer over-segmentation rather than under-segmentation. It would be more acceptable if maybe, for example, these 3 video clusters belonging to the same scene. Okay, this is more acceptable rather than we cluster many video shots together, but this video shot belong to different video scenes. Okay, we would feel more acceptable in the over segmentation case. So this would be characteristic we can refer to design the threshold T. So this is an example showing the inference of time constraint. So assume that we have a video and we have several video shots, and the shots identify with the same capitals belong to the that means they have similar visual content. For example, B1 have similar visual content with B2 and B3 and B4 and so on. And right now we have already do the shot change detection, and then we try to cluster. Okay, so if we set the time constraint T as 20 seconds, and suppose B1 and B2 have this similarity, so we will cluster B1 and B2 first. Okay, there's no problem here. And then when we try to find other similar video shots, we may find B3, but B3 cannot be clustered into the set as B1 and B2. Why? Because the temporal distance between B1 and B3 is larger than T, so that we cannot cluster B1, B2, B3 together. On the other hand, B3 should be clustered with B4 later. So with such time constraint, the final clustering result would be B1, B2, A1, A2, A3, B3, B4, C1, and D1. So we can construct an STG like this. B1, B2 is a cluster, and A1, A2, A3. So there is a directed edge from here to here, and another direct edge from here to here, and from this one we have direct edge like here, and so on. So we can construct an STG like this, and by finding the cutting edge, the final result of scene change detection would be we find this cutting edge. So we cut off this one and cut off this one. So we have a scene like this is one scene, this is another, and this is the third scene. So the final result of scene change detection would be like this. Okay, so this is one case. But if we also take the time constraint T as 20 seconds, but if when we start the clustering process, suppose B2 and B3 have this dissimilarity, so we cluster B2 and B3 together first, and then when we try to cluster B1 into the set of B2 and B3, that will not be possible because the time constraint T. So the final clustering result would be B1 alone, B2, B3, A1, A2, A3, B4 alone, because the time distance between B4 and the B3 is also larger than T, and the C1 alone, D1 alone. So we get an STG like this. And then when we cut off the cutting edge, we cut this one, this one, and this one. So finally, the scene change detection result will be B1, A1, B2, A2, B3, A3, B4, C1, D1. So you can see that for the same video, with the same shot change detection result, with the same time-based constraint, we got totally different scene change detection result. So this would not be a case we like to obtain. So how do we solve this problem? Here, the author proposed a refinement analysis. The idea is to make the time window more elastic. They will compute the duration of each story unit and adjust. Here, the story unit is the actually each story unit is corresponding to each video cluster. Okay, so given a video cluster or given a story unit, we will examine the next story unit by relaxing the temporal windows and reclustering the shots in these two units. So if there is at least one new cluster that contains shots from the two units, two story units are merged into one. We see the detail of the algorithm here. So given the initial clustering result, we will try to relax the time-based constraint and do reclustering. Okay, so first, given the initial video clustering result, we calculate the initial time-based constraint based on the first video cluster. And then we do a clustering on all the shots inside the first video cluster. And set initially we set U1 prime as U1. And then in the loop procedure, we first compute the duration of UN prime and UI. And then we sum the duration of UN prime and UI as a new time-based constraint. With new constraint, we do a clustering on all shots belonging to the union of UN prime and UI. And if there is a cluster containing a shot from UN prime and another shot from UI, then we said that these two video clusters should be merged together. Okay. On the other hand, if this is not the case, we just use the original time-based constraint to do clustering. Okay, so the main process here is the second step, and we have chance to merge similar video cluster together because we have relaxed the time-based constraint. So from the example we have mentioned above, this is the initial clustering result. With the refinement clustering, we will refine the clustering result like this, and we can use this to construct the STG. And finally, the result of scene change detection will be like this. So all the dialogue scene will be clustered together. So this is the first scene, and the C1 is the second scene. D1 is the third scene. In the second example, the initial clustering result is like this. Now the refinement clustering result is like this. So again, we get a scene change detection result like this. And we can see that with the refinement analysis, we have same scene change detection result from both cases. And this is an example showing the STG construct from the second frames. In this video, there are more than 25,000 frames, and each at the spatial resolution 330 by 240, and there are more than 300 shots. And the time constraint is set as 2000. The delta is set as 0.3, and this is the STG from, this is a big STG showing the structure of this video. And by finding the cutting edge, we can segment it into scenes. Okay, so the time constraint clustering of video shot is able to identify individual story unit, and we can use such story unit to construct STG. And we can, by the STG, we can do rapid nonlinear browsing of long video program. Okay, and in the following, we will conduct several experiments. The dataset used here, the detail of the evaluation dataset is shown here. So we have 2 sitcom videos, 1 cartoon, 1 movie, and 1 documentary video. And here are the detail of the numbers of frame, numbers of shot, numbers of cluster, and the numbers of story units. Here we show the performance variation of different clustering parameters. In the video frames, originally this video consists of 10 video scenes. Okay, and this is the corresponding meaning of these video scenes. And actually this it was manually defined. Okay, and with different time constraint t and the clustering parameter delta, we may have many significant different scene change detection results. And like this one, U1, U2, that means for the actual first scenes, our system think it consistent of 2 scenes, U1 and U2. So this is an over segmentation case. And for U3, our system detect that there is a scene here, and it's actually 1 scene here. And here is another over segmentation situation. For this scenes, Monica's apartment, this is actually 1 scene, but with such a parameter, we detect it as 3 scenes, scene number 4, 5, and 6, and so on. So comparing the performance obtained based on different parameter combination, we observe that smaller delta value result in more cluster and thus more story units. So by comparing these two, for example, with smaller delta, we will terminate the clustering first, and then we remain more story unit. Okay, and finally we will obtain more scene change result. Okay, so smaller delta will cause over segmentation. So this is one observation. But fortunately, we human beings prefer over segmentation rather than under segmentation. So of course, it would be not it is not good if the situation of over segmentation is too severe. Okay, so from this result, we can see that maybe this feature combination is good, and this will be also nice. Okay, so finally we see that when t is set as 2000 and the delta is less than 0.5, or t set as 3000 and the delta less than 0.3, that would be working very well. And in this case, this may be under segmentation because many of them, for example, the scene number 3 and number 4 are falsely merged together. They are merged together as 1 scene. So this case is under segmentation, and all others are usually over-segmentation. And to verify the performance of the refinement analysis, here we fix the delta as 0.3, and then we compare the result of when the parameter t is set as 2000 or the parameter is set elasticity. So here we can see that the final scene change detection result really improved. Especially we can see that the first two stories unit in scene 1 are merged into one. So originally, if we set the parameter fixed, the first scene will be over-segmented into 2 story units. But with elastic parameter, we will only have 1 story unit. And the number of story unit in scene 6 is reduced from 4 to 2. So here, originally, we have 4 story units, and right now we have only 2. So the effect of over-segmentation decrease. So in conclusion, this paper proposed an analysis based on time-based time constraint clustering, and they proposed the structure called scene transition graph that make us easily understand the structure of a video, and it may also helpful in nonlinear browsing. And we can also do scene change detection based on STG. And the identification, integration, and application of domain-dependent and the semantic feature tend to improve segmentation accuracy. And related techniques will be discussed in the future in this class.